Afternoon, everyone. Welcome to another Takeo Tuesday. And it's even Tuesday, which is a good thing because it's a Takeo Tuesday. Um, as many of you know, my name is Brett Zerba. I'm an applications engineer and a trainer here at the Takeo Comfort Solutions. And I'll be joined today by Rich Medairos. And Rich will be doing the main part of the presentation. Today's presentation is on Introduction to Air Source Heat Pump Systems. So, we're going to keep it nice and light and just to make sure we all learn what the different components are. But Rich will get into much more detail about that shortly. Before we get into it, we have a couple of housekeeping things. First and foremost, there's some people already raising their hands. Thank you very much. Who did that first? There, I see, I can't even stop there. But thanks for raising your hand. If you raise your hand, I'll know you can hear me and see. So there we see a lot of Ali is raising his hand, and Daniel, and so good. Thank you, Greg, Thomas. Appreciate that. So that's a good start. Good start. No handouts today, but we will 24 hours after today's presentation. You should receive an email with the recording, access to the recording from today's presentation, as well as a download for your PDH hour, certificate hour. Look for that. Get in touch with us. Funny story to tell. I was in the office yesterday, first time in 15 or 16 months, and I actually went into my office and I checked phone messages, and I had 18 of them. Believe it or not, I hadn't been responded to them. So I apologize if anybody on the call or on today's webinar had left me a message. But I changed my message, so it now says if you call, call my cell phone, 401-465-4911. That's what it says now. But anyways, thank you. So now if you do have an issue getting a PDH certificate, and you call me personally, I should be able to respond to make sure I can track that down. Hopefully that can all work out. Takeo Thermal Appliance Company, 101-year-old company, privately held. Johnny White Jr. is the current president. He's current owner, I should say. He's above president. He is third generation, so his grandfather started the company. His father ran it for many, many years, and Johnny's been doing a heck of a job with his senior management team led by Cheryl Merchant. And we are slowly, as a company, recovering, I shouldn't say recovering from the pandemic, but moving on from the pandemic. And yesterday, Rich and I were able to participate in a session at our facility, and it was the first time we had a guest in since the pandemic. Think about that, right? March of last year, I guess, is the unofficial start of the big shutdown, the 2-week shutdown that lasted a little longer than 2 weeks. But nonetheless, it was quite nice personally to be back in the office and get to see a lot of folks that have done a heck of a job for Takeo, continuing to make product for us, and just a phenomenal thing. So obviously I wasn't able to say hi to everybody or greet them as I would have liked, but just waving to them and nodding at them and saying hi and walking by them really meant a lot for me personally, to see those folks. So it was quite a special day. Actually, the president of ASHRAE came to Takeo yesterday and joined us and met with Johnny and some other folks, and we had quite a day with this gentleman. He's quite a very knowledgeable folks. He's from North Carolina, and he's a degreed engineer from North Carolina State, but he's doing a heck of a job, as you can only imagine. So, as I said, today's presentation is on heat pump systems, air source heat pump systems. Ask questions, we'll answer them as much as we can. And you know, most of you know the routine. We go back and forth, and the more questions, the better. And if we can't get to them, we will try to answer them down the road or tomorrow or whatnot. So just keep that in mind. Other than that, I think I've covered the ground rules. I introduced Rich Medairos, and most of you know Rich, and he is very anxious to get started. So Rich, take it away, my friend. Take it away.
Well, thanks, Brett, for that great introduction. Excuse me 1 second. Hold on 1 second here. So just a quick intro for myself, for those of you who haven't met me or haven't been on one of our Takeout Tuesday broadcasts. Again, my name is Rich Medairos, and I'm a mechanical engineer, and I'm one of the senior systems engineers here at Takeout. I spent the majority of my career on the consulting side of the industry. I am a PE, registered in a couple of different states, and I specialize in the engineering and design of HVAC systems, and I've been at it for several years. So today is all about the introduction to air source heat pump systems, and if we have a little time, we're going to touch base on water source heat pump systems. But many of the principles that apply for air source also apply for water source. So hopefully we'll have some time to cover both topics. So getting right into today's discussion, sorry about that. We're going to talk a little bit about air source heat pump basics. Heat pump COP and EER. COP stands for coefficient of performance, and EER stands for energy efficiency ratio. Hydronic air source heat pump system criteria. Then we'll get into an air source heat pump design using our HSS software. And if we have some time, we'll also do a water source heat pump with a boiler and a cooling tower. If we have some time at the end, and then questions. So let's get into the air source heat pump basics. I do have a little photograph here of an air source heat pump. We actually featured these units at the ASHRAE show. Where was the last ASHRAE show, Brett? Was that what, the one in Orlando?
Yeah, but that, believe it or not, it was right before life changed and shut everything down. So it was late January, early February of 2020
Yeah,
in Orlando.
So
Yes,
we
Florida.
featured the pre-production model of the air source heat pump at the ASHRAE show, and I understand that this unit will be available in the near future. So look for an announcement in the near future for our air source heat pump. But we're going to go through how they work and what they're all about. So it should be interesting here. Let me just grab a pen to make sure my pen is going to work. Let's see, let's choose a pen color. Red is good. Come back and grab my pen in a second. Okay. So here's a couple of photographs of what the air source heat pump looks like. And let's look at a couple of diagrams. So here is a basic heat pump refrigeration cycle. Now I can grab my pen while we walk us through here. So as the name implies, an air source heat pump is actually an air to water heat pump. And in this configuration, we're showing the heat pump producing hot water. So it has, it's producing 120 degree Fahrenheit hot water that it's sending out to the system, hot water supply. And the return water for this type of unit is roughly around 110 degrees. I'll put that over here, 110 degrees Fahrenheit. You can have a higher delta T, but for the most part, they run within that range. So someone might say, well, 120 degrees, that's not really hot. Wouldn't you need a higher water temperature? Well, as it turns out, the air to water heat pump, these units are designed to operate at a relatively low supply water temperature, which means that the terminal devices that you select for this type of system have to be sized based on an entering water temperature, somewhere between 120 and 130 degrees. Now, there are air source heat pumps that provide a higher water temperature, but the majority of them that are on the market today are somewhere between 120 and 130 degrees. And again, repeating, the terminal device like a fan coil or some other device that's used to heat the building would operate at an entering water temperature of 120 degrees. Now, certainly with radiant flow heating systems, they can easily operate between 100 and 110 degrees. So these work nicely with those types of systems also. So we have, in this configuration, we are showing a refrigerant to water heat exchanger, right here, and that in this configuration is the condenser. So let's start at the discharge side of the compressor. So here's our compressor over here, a little diagram of a compressor. So the compressor changes the refrigerant into a high temperature, high pressure gas. That high temperature, high pressure gas enters the condenser, and then when we have our water coming into the refrigerant to water heat exchanger, it's going to cause that high temperature gas to condense and give up its heat to the water as it flows through the system here. So when the fluid leaves the condenser on the refrigerant side, it's now a high temperature, high pressure liquid. And it has condensed, as I said, and that allows us to heat the water from roughly 110 degrees through the heat exchanger. I'm going to put a little squiggly line here, and up to about 120 to 130 degrees. So I've shown 120 degrees today. And then the refrigerant continues along its cycle, passes through the expansion tank, and this is when it enters the evaporator as a low temperature, low pressure liquid. It's actually a liquid vapor mixture. And in order for it to extract heat, we could extract heat from ambient air. Ambient air, let's assume, is around 17 degrees Fahrenheit. We can actually extract heat from that air. So the temperature of the refrigerant at this point here has to obviously be lower than the ambient temperature in order to extract heat. And so we're just going to make up a number and say that that low temperature liquid is somewhere around 10 degrees Fahrenheit. I'll just kind of put a number in there so you can get an idea. So that means that the low temperature liquid will evaporate, and as it evaporates, it absorbs heat from the outside air, and then it becomes a low temperature, low pressure gas that enters back into the compressor over here. So that's how we can get the refrigerant cycle to extract heat from a relatively low ambient air and generate hot water, which is sufficient enough for heating a building. So any questions about the basic heat pump refrigeration cycle that we've got here? Anybody have any questions out there, Brett?
It's question / comment. It's air source because of that 17, the ambient air coming in instead of water being there as one of the parts. It's air, right? That's why it's an air source.
That's correct. Yeah.
Someone said.
Yeah, and you know, probably most people might be familiar with an air-to-air heat pump. They're fairly common in homes, especially in the South. I have one in my home down in the South. And they, instead of having a refrigerant to water heat exchanger, they would have a refrigerant to air heat exchanger. And then they would make warm air and supply that warm air to the house for heating in the wintertime. Okay. Let's erase all of that stuff.
So roughly what does the 17 degree Fahrenheit ambient air get cooled to?
So what happens is that the ambient air at 17 degrees, when the temperature of the liquid down here is, let's say we said about 10 degrees, is usually about a 3-degree approach. So that means that it could go down to around 13 degrees. So it enters around 17, leaves about 13 degrees. Let's see, did I say, yeah, 10, yeah, about a 3-degree approach, 17 minus 3, 4 degrees, I'm sorry. So it would leave here at 4 degrees. I think I said that wrong one more time. I meant to say 14 degrees, right?
Right.
17 minus 10, yeah, about 14 degrees. Okay, does that answer that question?
Yep.
All right, so we're going to look at another diagram, only in this case we have 2 diagrams. It's really a little bit more detail about the reversing valve. So what I just showed you a moment ago was the refrigerant cycle. Now this particular one has an air to, let's go on the left side here, as a refrigerant to air heat exchanger. So this guy on the left, I'll grab my pen one more time. This guy on the left, I just showed that in the previous picture as an air to water heat exchanger, but here I'm just showing it as, I'm sorry, as a refrigerant to water heat exchanger. But this one is a refrigerant to air heat exchanger. But what I'm really interested in, which is why I'm showing this diagram, is the reversing valve. So it leaves the compressor as a high temperature, high pressure gas. It goes through the reversing valve and then goes into the condenser. This is the same cycle I just showed you, and then through the expansion valve, and then through the evaporator, and then back into the reversing valve into the compressor. Now, if you'll notice, this reversing valve can then rotate, and when it rotates on the picture on the right, you'll see that it changes, and now the high temperature, high pressure gas is diverted through the rotating reversing valve into the condenser, which is now outside, and that allows us to make the evaporator inside. Now we can make cool air or cool water. So that shows you how the reversing valve can take a conventional heating cycle on this side here and convert it into a conventional cooling cycle over here. So instead of physically swapping equipment around, which of course is not practical, but we have this reversing valve that changes the direction of the refrigerant, where before the refrigerant went to the condenser, which was responsible for making hot water, in this case hot air, but in the previous diagram hot water, and then absorbing heat from the outside air. And then the reversing valve then redirects the refrigerant to change the functionality of the two components. Okay. Any questions about the reversing valve?
Nope.
And then we also have a little diagram here, which is the classic pressure enthalpy ideal refrigerant cycle. And as you can see, the compressor, which is shown over here on the right, compresses the refrigerant from a low temperature, low pressure gas into a high temperature, high pressure superheated vapor. And this from point 2 to point 3, although we don't have any values assigned, along the x-axis is the enthalpy of the total energy. So this is the work that the compressor has to do from point 2 to point 3. And once it gets to point 3, the refrigerant passes through the condenser and changes from a high temperature, high pressure gas into a high temperature, high pressure liquid. And so as it goes through the condenser, it is actually rejecting heat. And then when it comes back to the expansion valve, you'll notice that at point 4 here, it's a saturated liquid, and it passes through the expansion valve. And that's what I was saying a moment ago, that the refrigerant is mostly liquid, but some vapor. So this portion over here is the vapor, and this portion over here is the liquid. And then the cycle completes itself. So in terms of energy, you can see that the amount of energy that it takes to create the compression is relatively small. Let me kind of draw a vertical line here. Even though I don't have any values, you get the general idea here. So because the enthalpy in this case are vertical lines. So there's the change in enthalpy due to the compression. And then if you look at how much energy can be rejected by the system, then the enthalpy difference is this whole value over here. So if I extended that, whoops, should have extended that over here. So if I extended that line over there, you would see that the enthalpy is now this difference for the total amount of energy, and then this small distance over here for the compression energy or the work of the compressor. So the work of the compressor is relatively small compared to the amount of heat that we can either reject or absorb either through the condenser or the evaporator. And that's important when we get into the next part, when we start talking about the coefficient of performance. Any questions about the refrigerant cycle? I just say one thing I would say is that since our main function, I mean not function, but our main interest is on the hydronic side, I'm just presenting the refrigerant cycle so you can get a rough idea of what it's all about. So if you want to do some research on your own in terms of refrigerant cycles, there are some great explanations on YouTube. They're very, very good. But as far as TACO is concerned, the refrigerant cycle is a packaged part of the system. What we're really interested in is what happens to the water as we circulate it in the system. Okay. Any questions, Brett, out there?
Someone's asking, can you explain what enthalpy is essentially?
Well, enthalpy is the total energy that the fluid is doing. So in other words, and it's in BTUs per pound, if it's in the imperial units. So enthalpy is always BTUs per pound. It's total energy of the working fluid. And this is called a pressure enthalpy diagram. So the horizontal lines are constant pressure, the vertical lines are constant enthalpy lines.
Excellent.
Okay. Go to the next one. So let's start talking a little bit about COP and EER. So let's, COP stands for the coefficient of performance, and by definition, it is the ratio of useful heating or cooling provided divided by the work required. So it's the heating or cooling provided divided by the work required, and it's in the same units, So in other words, it's the capacity divided by the energy input. So let's look at an example. So if we were given a capacity of 45,163 BTUs per hour, and the energy input was 5,510 watts, because we want the capacity divided by the energy input, but they have to be in the same units. So we have to convert a couple of these units. So let's find the coefficient of performance. So we first have to take the 45,163 BTUs per hour and divided that by 3,412 BTUs per kilowatt hour, which in this case is 13.24 kW. And so now we can take that energy input is 5,500 watts divided by 1,000 watts per kW, which is 5.510 kW. So that's the energy input. So we take the capacity, which is kW now, 13.24. We've converted the 45,163 BTUs per hour into kW, and the energy input was given to us in watts, so we simply divided that by 1,000 to come up with kW, and now the coefficient of performance is equal to the capacity divided by the energy input, which in this case is 2.40. So the coefficient of performance in this specific case is 2.40. So if we look at, I took these numbers directly off this chart, and if you'll notice that, let's see, I think it's, yes, it's over here. So with a supply water temperature of 42 degrees Fahrenheit, if I'm generating a supply water temperature of 42 degrees Fahrenheit, and here's my capacity of 45,163, and there's my watts. And I just did a calculation that showed you that the coefficient of performance was equal to 2.40 in this case. So this is the manufacturer's data, which I just calculated for you. So let's just go back to the previous screen so you can see. Again, I'm using the 45,000 as the capacity, 45,163, and the amount of power consumed is 5,510 watts. Going back to that previous calculation, I converted the capacity into kW, and I converted the input into kW, divided the capacity by the input, came out to 2.4, and that's exactly the same number that's published by this manufacturer. Any questions about how I calculated the coefficient of performance?
Nope. Someone's asking if he lives in Fairbanks and he's wondering if you know of any air source heat pumps with a COP above 1 at -20.
I'm not personally aware of equipment that has a COP above 1 at -20. I do know that there are several manufacturers that are experimenting with CO2 as a refrigerant. And some of the initial, let's say, research and development indicates that they may be able to get COPs above 1 at relatively low temperatures. And I'm not going to say that they can get above 1 at -20 degrees Fahrenheit. Did you say minus? Did he say -20 or 20?
No, minus.
-20, yeah. I do know that the CO2 refrigerant-based units can produce a higher temperature water and get a COP above 1 at relatively low temperatures, but I don't know exactly what those are. I don't think there's that much in the way of published data yet for that equipment. So yeah, so I guess the answer would be I'm not aware of one, but some manufacturers are getting close to those kinds of values, and I would expect in the next year or so, even probably less than a couple of years, but certainly within the next year, we should start to see some manufacturers publishing that kind of data. Any other questions, Brent?
Oh.
Okay, let me just go back here. Yeah, it was that. Okay, so now let's look at what happens to, so here's the same, by the way, information that we just looked at. So in other words, we went back here. This was the cooling capacity. We're making 42-degree water with a 95-degree ambient air temperature. And if we look at that on a graph, so the capacity is in the upper half of the graph over here, and 42-degree Fahrenheit water with 95-degree ambient temperature. Follow 95 up to where it intersects this dotted line here. You can see that this is 40,000, that's 48,000, halfway is 44,000. So you can see that that value is probably around 45,000, and that's consistent with what's on that chart over here, around 45,000. And then the COP, again at 95-degree ambient, we're producing 42-degree Fahrenheit water. You can see the COP is around 2.0. So that's the cooling performance. Let's look at the heating performance for the same unit. And so we're looking on the left side of the chart this time. And at the left side of the chart, let's say we're down here to 17 degrees Fahrenheit. So let's go back up here. So let's say we wanted a supply water temperature of 120 degrees, and we had an ambient temperature of 17 degrees. We could provide from this manufacturer 28,500 BTUs per hour. And if you notice, the COP is 1.59. So it's, even though it's 17 degrees, it's still above 1, which is really good. And so if you look on the chart, again, this is 15, 20, so it's about 17 and a half. So it's about 17 degrees. And where it hits the dotted line, not the dotted line, but hits the bottom line here, that's the 120 degrees. So it produces 120 degree water with a COP. So there's 1.0, and then halfway up would be 1.5. So it's about 1.6. And I think that's, let's go back to that previous. And yeah, it's 1.59. So you can see that as the ambient temperature begins to drop off, the capacity of these air source heat pumps drop off, and also the COP begins to drop off. Now, if you'll notice, if we're only making 100-degree water over here, that would be this top dotted line here at 17 degrees. That would mean we'd be making, well, there's 32, that's 40,000. So the difference between those two is 8,000. So that would be 36,000. So this is at 17 degrees would be what, around 33,000. So we can go back to that other chart at 100 degrees Fahrenheit, 17 degrees. So you can see right there it's about 33,000 BTUs per hour. And the COP begins to improve, even though the ambient temperature is still 17, but if we're making water at 100 degrees, the COP improves a little bit. Okay. So hopefully you got the idea on how to look at both a graph and a chart and how to calculate the COP. So the energy efficiency ratio is similar to the COP in the sense that it's the ratio of useful cooling divided by the work required. It's the same basic concept. However, when it comes to the EER, energy efficiency ratio, the capacity is in BTUs per hour and the energy input is in kW. So in this case, let's say we're given a capacity of 7,400 BTUs per hour and the input is 456.7 watts. The EER is equal to, we'll take the BTUs per hour divided by 1,000 BTUs for MBH. That's 7.4 MBH, and the energy input, we can convert that into kW, 0.467 kW. So 7.4 divided by 0.4567 kW is equal to 16.2. And here's a little interesting fact, which we can do for you. If you take the EER, which we just calculated in this little example here, you take the EER, so the EER is a weird number, but it's one that we use in the industry. It's essentially the BTUs divided by the kW, or MBTUs. If we take the, oops, that's an R, not a P. EER is actually equal to the COP times 3.412. So one of the things about EER, if you're trying to compare the COP of one machine versus another, but one happens to be in EER and the other one happens to be in COP, if you take the EER is equal to the COP times 3.412. And the opposite is true. So let's do it this way. The COP is equal to the EER. Trying to get my letters out, Brett, without messing it all up here. How am I doing?
Okay.
Divided by 3.4. There we go. 3.412. So let's do the math out here. So if our EER is 16.2 divided by 3.412, then our COP would be 4.7. So those where those numbers come from. Isn't that interesting? Any questions about that?
No.
So EER and COP are actually sort of the same number. They use different units, and to convert one to the other, this is the equation that you use. All right, let's try erasing all of this wonderful stuff. To go back, the erasing thing is never easy on this.
No.
Okay. All right. So the next thing we want to talk about is a hydronic air source heat pump system criteria. So we're going to actually design now an air source heat pump system, but we have to establish some of the criteria. So in this case, we have to establish what the load is, and that you get that from a heating and cooling load calculation. We always recommend that you do a detailed heating and cooling load calculation. And if you need some software to do that, you can get that from us. Actually, I'll show you where to get it right here quickly. You can go to our website right here. Let's see if it clicks on, there it goes. And then we can go to software and our, let's see, here it is, the load tool. So if you can right here, which is the one on the right. You can download the load tool. I'm not going to do that right now, but that's how you get to it. And it's a heating and cooling load calculation. And it's a fairly simple and straightforward, easy to understand, easy to use for estimating your heating and cooling load calculations, or heating and cooling loads rather, using this software. So the software is available from us for no charge. Okay. So we also need to know the ambient air temperature. In our case, we're going to be interested in both the heating and cooling, supply water temperature that we're sending out to the system, the return water temperature, the fluid, and the flow in gallons per minute. So what does that look like? Well, in our case, I have a building that needs 192,000 BTUs per hour. I have an ambient air temperature of 0 degrees Fahrenheit for the winter, 95 degrees Fahrenheit for the summer. That's the, let's go back. The ambient air is the outside air. That's the temperature. I'm going to extract heat from 0 degrees Fahrenheit in the winter, and I'm going to reject heat to 95 degree ambient air temperature in the summer. Supply water temperature for winter operation is 130 degrees Fahrenheit. For summer operation is 45 degrees Fahrenheit. And the return water temperature, 120 for the heating season and 55 for the cooling season. And in both cases, it's 10 degrees delta T. The fluid in this case is 30% propylene glycol, because remember, our unit is an air to water heat pump. And so it's sitting outside in the weather, and the water glycol solution is outside. So to keep the to keep the fluid, in this case water glycol, from freezing, that's why we use the propylene glycol. And we've estimated the flow to be 38.4. I'm sorry, the flow. Boy, I messed that up, Brett. Look at that. I put the units in there as degrees Fahrenheit. I'm going to fix it in real time here. GPM.
Awesome.
How's that?
William will be happy.
Yeah. So when we look at this later, we say, whoa, geez. Okay. So here we have, I've decided to divide the load into 4 units or 4 components. So in other words, let's go back. We had 192,000. If I take that 192,000 divided by 4, then each one of my air to water source heat pumps is going to be roughly 48,000 BTUs per hour. So I have 4 units, and each one of these will produce either cold water in the summertime, in this case 45 degrees, or hot water in the wintertime, in this case 130 degrees. And I've set this up as a primary variable flow. So I have the circulators, and I've got these 2 valves here showing where it connects to the rest of the system. So I broke it up into 2 pictures so it'd be easier to read. If I had the whole thing on one page, it becomes very tiny and difficult to look at. So then it goes out. There's the air source, heat pump design, outside components. Okay, so now here are the heat pump design inside components. So there are those 2 valves again. So there's my supply water temperature, and going to my fan coil. In this case, it's a very simplified fan coil system. And I've got 2 floors with 4 fan coils on each floor. And I'm using a conventional piping system to accommodate that. So I'm supplying 45 degree Fahrenheit chilled water in the summertime from my air to water heat pump, and in the wintertime 130 degrees. Now again, what I said, just like I said earlier, the heat pump that's producing the hot water is sending the hot water to the terminal unit, in this case fan coils. So the fan coil has to be selected for an entering water temperature of about 130 degrees Fahrenheit. That's my design condition. So that gives you a quick snapshot of what the actual system configuration is going to look like. Brett, do we have any questions that we need to field right now?
No, we're in good shape question-wise.
Okay. So we actually do have a little time. So we're going to build what we've just shown you physically is an air to water heat pump system. Now we're going to show a more conventional water to air heat pump system using a cooling tower and a boiler, and I'm going to build that system by using the HS2 software. So with a little luck, I'm going to launch my HS2 software, and it's going to launch the first time successfully, Brett. I've got my fingers crossed here.
Come on now. Come on, baby.
Come
Rolling
on.
the dice. The
We have
dice are
to
rolling.
cheer it on. And so, yeah, look at that. So I'm going to go over here to my wizard in a minute. There we go. And I'm going to build a system. And it's going to be a, let's make it a load match system, heating and cooling. And I'm going to ask Brett to help me out if it looks like I'm clicking something incorrectly, Brett. And I want to I'm going to build.
Go back now, Rich. Do you want are you designing, what are your terminal units?
They're water source heat pumps.
Then you want to choose the next block down,
This one here?
combined schematic. Yeah, otherwise the one above it represents fan coils. You would have one heating drawing and one cooling drawing.
Okay, great.
Separate schematic. Yep.
So we'll pick that. And
Yep.
again, similar to before, I'm just going to have 2 loops, and I'm going to have 4 terminal devices per loop. We'll put the load orientation above. And in this case, it's going to be a heat pump. And we're going to put in here 48,000 BTUs per hour for the cooling, and the same thing for the heating, just for the fun of it, keep it the same. Oops, sorry, we'll put in 60,000 for the heating. And then we'll go for the heat source will be a boiler, and then for the cooling source will be a cooling tower. And in a minute, we're going to talk a little bit about the cooling tower. So for the boiler, I'm going to make it 2 boilers, each boiler sized for 50% of the load. And then I'm going to use 2 cooling towers, each cooling tower again sized for 50% of the load. And I'm going to make it a primary secondary loop for the heating and primary secondary loop for the cooling. And we're going to use a hydraulic separator to show what that looks like. And the vertical inline pumps for the secondary pumps, I kind of like to have 2 of those, and each one sized for 50%. That looks good. If you see anything weird, Brett, let me know.
Yep.
It looks good.
Watching you like a hawk.
Watching me like a hawk. Good idea. All right, so we're going to zoom out a little bit so we can see what's going on here. So, so to give the pumps a little bit resistance to overcome, I'm going to just arbitrarily, just for our discussion today, take the hydronic pipe and say each section of pipe is going to be 20 feet. Now, it's a little bit bizarre, but I want something in there for pipe's length so that it'll calculate some pressure drop. So I'm going to go over here and do some selection, and hopefully that worked. Yep. Okay, so now we have a conventional, in the previous discussion, it was an air to water heat pump, and this is the opposite. This is a water to air heat pump system, or sometimes referred to as a water source heat pump system. And in the water source heat pump system, let me, sorry about that. Let me shut off my email. If I don't do that, I'll get some. So let's look at the primary secondary loop. Zoom in here a little bit on the heating side. So in this particular case, the water temperature being generated by the boiler is around 70 degrees Fahrenheit, and that 70 degrees Fahrenheit is trying to heat up that water through the primary secondary loop. Actually, something happened here, Brett. How come that happened? Well, I don't really have an explanation for that right this second. But anyway, if we follow the loop around, let's say here are the secondary pumps. The secondary pumps are sending the water to the water source heat pumps, and we're using a single pipe system. So we're using a load match circulator to send the water to the water source heat pump. The water source heat pump is acting like a fan coil within the space. So it's actually supplying either cool air or warm air, cool air for the summer, warm air for the winter. And the nice feature about this system is that this particular heat pump number 1, for example, could be in the cooling mode, and heat pump number 2 could be in the heating mode. So you could have simultaneous heating and cooling in this type of system. So this is not a changeover. You get simultaneous heating and cooling. Why are these temperatures messed up, Brett? Do you have an idea of what's going on there?
I'm not 100% sure. I think it has to do with the summer and winter seasons.
Yeah, apparently I didn't specify that correctly. I wonder if I did this again, Brett. Let me try this one more time without putting in the
5900.
in the hydraulic separator, if that fixes it. I'm just kind of interested to see how HS2 handles this. Let's go down here.
That was hard to design a second system.
Yeah, wasn't that quick?
Still got one.
Yeah, I think this one looks like it's going to work. Yeah, this looks like it's going to work. I'm not sure why the other one didn't work, but this one I think will.
I would suggest heat pump system wise, this design is probably a little more traditional than the one where you're using a heat pump for generation of the fluid.
Yeah, this is the more common one that we see out there, although we think that the air to water heat pump will gain in popularity because basically it does not use a fossil fuel. It's an all electric system, where this system implies that we're using either one of the 3 major fossil fuels: natural gas, propane, or oil in this particular case here. So we'll do a quick equipment selection. So here we have the circulating loop, and the circulating loop wants to have a maximum temperature of about 80 degrees and about a minimum temperature of about 70 degrees. So we inject some hot water into the loop to maintain the minimum temperature of around 70 degrees, and then the cooling towers are used to maintain the maximum temperature at around 80 degrees. Oh, I still have a
right.
hydraulic separator. Apparently I didn't uncheck that. But as you said a moment ago, we can actually fix that very, very quickly. We can just go back here and do this. And this time I'm not going to spend any time explaining what I'm doing. I'm just going to click on everything till I get here and deselect the hydraulic separator. And then now I have a system that I believe is more typical of what we would see. And then again, I'm going to put an arbitrary length of pipe just so that it has something to calculate for pressure drop. And it's just arbitrarily put in 20 feet for every section of pipe. And then I can do the equipment selection over here. And now I have an air to water, a water source heat pump system. And as Brett pointed out a minute ago, this is probably the most common configuration that we see today.
So
the one that we talked about originally is probably one that's going to gain in popularity.
So what some of the differences I see on folks when I work with folks is when I look at this type of design right here, right? We have a cooling tower, pretty traditional, especially for a water source heat pump type of job, where the heat pump is in the zone. So the cooling tower can provide that water temperature that the heat pumps love. And then when it comes to the heating, to inject heating, many systems, I see a boiler like Rich shows. Sometimes I see electric heat pumps for heating. It depends on where you are in the country or what your zones are. So there are heat pumps out there, right, Rich, that have heating elements that are electric instead of that might boost it up that regard. So I do see that out there as well.
Yeah, that's very, yeah, especially like you said, in kind of the center section of the country and also in the south. And then we tend to see fossil fuel. Usually natural gas is the most popular, but not
But
exclusively
I tell you, you
in
get
the
north of
north.
the Mason, you get north of the Mason-Dixon line and north of the border, you definitely want a backup boiler on a heat pump system,
Yeah,
for sure, because there will be times when that probably every heat pump is calling for heating, and you need that backup at that point. Wouldn't you agree with that, Rich?
yes, yeah.
Yeah. And then we also see for systems like this in different parts of the country, and again, or in the world, country, whatever. I'm more familiar with the U.S., in Canada, North America. Instead of a cooling tower, and even maybe instead of a boiler, sometimes it's backup. We see ground source systems where people put in wells as well, wells as well.
Wells as well.
Now that's a new one. So that's a possibility as well. Too many wells. I'm
Too
getting
many
all
wells.
messed up. Too many wells. So we have a
Oh,
great
well.
question. We have a great question, Rich. Why
Yeah.
why are you showing a circulator at each heat pump?
Well, this is our load match system design, and the nice feature about this is that look at it. It's a single pipe from left to right here. There's only one pipe, horizontal pipe on each floor, and then we use a bridge, which we call a twin T. I'm going to zoom in to this little twin T. Hopefully, you can see that. And we're using a circulator instead of a control valve. And the reason we call it load match is because we're matching the GPM of the circulator. In this case, it's 20.2 GPM to each of the individual heat pumps. And so we can save on pumping energy, and we can also save on piping because instead of having a supply and return pipe on each floor, we only have one pipe. So we call this our load match system. Generically, it's known as a single pipe system. So
Actually,
that's why
Rich.
we're using circulators.
Actually, Rich, you could you could use that wizard, and you could design a two pipe system showing the traditional curve control valve just by changing the question, changing it. That's how
Yeah,
easy this.
go back, like Brett said. We're gonna Brett, stop me, make sure. Wait,
you're just going to change that first chance right there.
Just that one, right?
Yep.
And leave everything else the same.
Yep. Just be careful
So
when you get to the
the
end.
magic of the HSS software, the amazing software. We're going to look at a conventional system using pumps as the main circulators and two-way control valves, similar to what we just talked about. So in this case, we have two pipes. We have a supply pipe here and a return pipe on each floor. And then for the branch piping that goes out, we have a two-way control valve, which adds system resistance, which is why the circulator system or the load match or single pipe system uses less energy because there's no control valve to overcome the resistance. There's just the heat exchanger inside the heat pump, or in this case, the heat exchanger inside the heat pump here, but there's no control valve. So
one of the biggest zoom back in on the two pipe design. One of the biggest differences in the two pipe design compared to the single pipe design is the entering water temperature to the heat pump. There's other differences, but from an engineering standpoint, that's one of the biggest differences. If you look at this drawing that Rich is zoomed in on, the entering water temperature for the heat pumps, when it's all heating, is 70 degrees, and all cooling, it's 80 degrees. Okay, it's the same as we all are used to. But if Rich zooms or scrolls up to the single pipe, you'll notice the heat pump, the entering water temperature changes as it goes down the line, as that single pipe. And we're not getting into the whole design philosophy here, but that is one of the more technical differences between the two. There's obviously mechanical differences, right? Less pipe, electrical differences, whatever, but that's the biggest technical difference. But think about a heat pump. As Rich was showing you some of the numbers on a heat pump, entering water temperature, how much it affects the actual output of the heat pump. You can look at a design, but it's very, very minimal percentage-wise. So if you need 60,000 BTUs, boy, if you go in at 70 degrees or 67 or 65, you're going to be pretty close to what you need there. So I digress. Sorry I took it away, Rich. I got
No, that's great. I think we're actually at the point where we could take some questions.
Yeah,
We're just about out of time.
We have a great question. Is the HSS also a free download?
Yes. In fact, let's go to the website again one more time. I'm going to do it from start to finish. So I'm going to go to the TACO website, which is tacocomfort.com, and then click on right in the middle of the screen at the top where it says software, and then HSS, Hydronic System Solutions Software. And you'll notice the second one from the left, Hydronic System Solution, HS Hydronic, exactly the same software that I just used. I won't download it because it's already on my desktop. You just click on download, you fill in a couple of things. Well, I won't download it, but I'll show you the next screen. You just fill in your name and the company name and the email address, and then click download software. In just a matter of seconds, you can get the software. And you can do all the wonderful stuff that I just did and that Brett helped me with. Brett's the expert, and I'm just one of the users here. So yeah, that's how you get it.
We learned yesterday that the president of ASHRAE is a big fan of this software, and he uses it to design some of his hydronic systems and steam systems. He may need a different version.
Yeah,
but
it makes designing hydronic systems a fraction of the time of what we used to do it manually years ago.
So,
of course, when I use the term years ago, that was before electricity, Brett.
Slide rule days, no air conditioning.
Slide rule, yeah. Before electricity, everything was written on the back of a magazine.
I still remember that back in the day when I first started. I graduated from the University of New Hampshire in 1981. My first job, people could smoke in our office. I mean,
yeah, that's that you're right. I mean, I remember that too. People would, they'd sit at their desk and they'd work on drawings and they'd smoke like crazy. I remember the day that we made the transition. This woman went to the owner of the company and said, "I'm not going to work here anymore if people are going to smoke cigarettes." And within a couple of days after that complaint, all the cigarettes disappeared, and people had to either smoke outside or they went to a designated smoking room. They were no longer allowed to smoke in the open office area, and that was a revolutionary thing. But today, it's considered to be normal practice.
Funny story to add to that. My daughter in 2013 moved from the East Coast to the West Coast, and her and I drove across country. So, we took our time and stayed in different places. Well, the first night we stayed in a place in Virginia, and we went out to get something to eat. And that's the first time in her life. She was born in 1991. That was the first time in her life she had ever been into a building where people were smoking. They still had the smoking section and a non-smoking. You remember that when they used to separate them?
Yeah, I wonder, back in those days, if they had COVID, if they had the COVID pandemic, way back when they allowed people to smoke cigarettes on airplanes, if you'd have to wear a mask that had a hole in the mask so you could put your cigarette in. I don't know. Well, anyway, we're just about out of time. Do we have any last-minute questions, Brett?
No, our good friend Warren Juergen says, can you compare and contrast air-to-water heat pump systems to a water source heat pump system? And I think we did that. I think we did work. I think you did a good job of working that in, right? It's really the generation equipment is the big difference, I would say.
Yeah. Yeah, we're going to see more and more of these air-to-water heat pump systems out there. As the equipment gets developed, we'll be offering air-to-water heat pumps shortly. And again, one of the nice features about them is that they're all electric. And under the right circumstances, you can get a substantial amount of usable heating or cooling out of a relatively small amount of power input under the right circumstances. So yes, more and more of these as they become developed.
Excellent job, Rich. I think we're in good shape question-wise.
You're in good shape. So we're at that point where I'd like to thank everyone for participating in TACO Tuesday today. And if you have any further questions, type them in now. If not, any questions that were left unanswered, we'll answer them over the next couple of days. So any last questions out there, Brett?
Is TACO going to make water source heat pumps compete with Water Furnace and Climate Master?
I do not believe that we are moving into the water source heat pump market. I don't believe so. I believe we are moving into the air to water heat pump market. And we will be, like I said, we did have the unit, the pre-production unit shown at the ASHRAE show. And I believe we're either a few months away, probably less than a year away from introducing it into the marketplace. So be on the look for it. Air to water heat pump. The heat pump, as we said in this little presentation, will generate both chilled water for cooling and hot water for heating.
Excellent.
Pretty cool stuff.
Excellent. Excellent. Excellent, Rich. Thank you very much. Thank you, everybody. Appreciate your time. In 2 weeks, we will be doing a focus on the vertical inline pumps, TACO KS, KV, SKS, SKV. More of a detailed, I won't say analysis, but a breakdown of, and all the details associated with it, material of construction and whatnot. But there's probably some new information for many of you on the KVs and the KSs, but as well as the SKVs and the SKSs. So hopefully we'll see you back then. And then in July, we got a little change of pace. We've been trying to do 2 of these a month, but we're going to skip that first week of July, the week of July 4th. And Rich and I are going to enjoy ourselves like everyone should. But anyways, so the only commercial one in July currently planned is actually going to be an HSS one. We're going to revisit HSS, see some of the new things, make sure we can understand how to download it. And we're going to design 5, 6, 7 systems. Boom, 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 boom. Rich and I are going to design systems left and right. And maybe we'll ask you folks to send what kind of system you want next, and we'll try to do that. But we'll see. We'll stump the teacher. Stump the teacher. We like that. But again, thanks for your time.
It's probably a good thing to mention that there'll be an announcement fairly shortly about our TACO After Dark commercial edition. I believe we have the first TACO After Dark commercial June 23rd at 7 p.m. on East Coast time. And I believe the next one will be June 30th, 7 p.m. East Coast time. And then the third one will be July 7th.
No. We're going to the next July. We're not going to do one that shutdown week. We're skipping that
okay.
week.
So I'll just say June 23rd and June 30th, and we'll figure out the next date.
July 14th.
July 14th. All right, put that down.
So the residential guys have been doing TACO After Dark for a while, but they're a lot younger than Rich and I. So Rich and I have to stay up a little later.
No, I mean we're only in our 30s, right?
That's true. We lose time every year. But thank you, everybody. Appreciate your time. Look for your emails tomorrow. And if you don't get them with your PDHs, let us know and we will take care of it. See you in a couple of weeks. Bye, everybody. Thanks, Rich. Great job.
Bye-bye.